So today we will talk about logs translator. So I've worked on multiple cluster translators also in Gluster, but I personally find this translator to be the most complex in glusterfs. It is very easy to make mistakes in this translator and get into deadlocks. So I've debugged quite a few such things early on, maybe in early 2000s. There were quite a few such bugs that we had to fix to make this stable. So every time somebody sends a patch in this translator, I'm really nervous about what kind of bugs it will lead to, because it is not obvious the kind of bugs that can come. Like very subtle bugs will start coming. So let's try to understand the high level functionality of this translator and some code. Initially, I thought I will only do 2 sessions, but looking at the complexity of this translator, maybe 3 sessions seemed better. Today we will, okay, so this is the scope. So we'll try to find out why we needed logs translator in glusterfs, what are the kinds of logs we have in Gluster, some functionality that is exposed by logs translator for clients or even internal clients, how they use it. The most famous consumers of logs translator are AFR and EC, and I think in the last 2-3 years, even DST started doing locking. So that is what we'll try to cover in this session. Okay, so first thing, why do we need logs translator? So as most of you guys probably know, in glusterfs we have replicas and even erasure coded volumes. Every time we are trying to modify any data, there is always this chance that some other client can also modify the same data. So if you have I can probably give you an illustration. Let's say, okay. Right, okay, let me create this one. So let's say we have this /mntr3. This is a replica 3 volume. So now when you do it, so you can, let's also mount it. Let's just, okay. So it can so happen that one process is doing touch A, another process is doing mkdir A. Okay. So when somebody executes these 2 commands in parallel, or these 2 system calls, which actually create the files, be it mknode/create here and mkdir A here, only one of them should succeed, and it should be completely a file or a directory. It should not be on what is this? Like when we execute these parallel operations, it should not be that on some bricks it is like a directory and some bricks it is a file. So we can't have that for consistency, right? So you need synchronization between 2 clients. Client 1 is this mntr3 and client 2 is mntd3. Similarly, let's say you are trying to write to a file in the same region. We can actually do something like touch C. If you do echo ABC from C, this one, and let's say echo df from this one, C. If you do this in quick succession, also you should generally have that same data. So this is important. Okay, yeah. So in both of them, you should have same data. So to get this synchronization is where the client translator, these replica translators or DST or EC translators, they need to take necessary locks so that only one of them will be allowed to do the updates. So that is the purpose of locking in glusterfs. And these logs translator, okay, I think that is in the next slide. So what are the kind of locks that are supported in logs translator? So as you can see that, general operations that we are doing is like, creation and deletion of files are trying to write to files. So synchronize between these two types, we have entry logs where you can do namespace synchronization. So you can say that, on this directory, this will be like, root of the mount will be /, so like 000 and 1 at the end. That is the GFID for the root. In that directory, you will take a lock on the name C. Okay, and when the same like mkdir gets executed also. Okay, sorry, here okay, maybe we can take this example, touch C and mk. Okay, where was that? Okay, let's say somebody is doing mkdir A and here somebody is doing touch A. So this client will also try to take a lock on this name A, and this client will also try to take a lock on name A. Whichever gets the lock successfully, that operation will actually go ahead and it will be successful. Like if this guy gets the lock successfully, it will be a directory. If this guy gets lock successfully, it will be a file. And the next guy, like once the operation is successful and this guy doesn't unlock, the next operation will get an exist, which is like the name already exists. That error it will get. So that's how you kind of have consistency. Only like you are basically serialized the one after the other, and you avoid inconsistencies in the file system. So that is for the entry locks. Okay, so you're basically taking lock for entry creation, which is like a named locks in a directory. Then you also have inode locks. Inode locks actually are something like almost similar to POSIX locks, but not completely. We will also cover POSIX locks in later sessions, maybe the third session, where the functionality and the behavior that is offered by POSIX locks is a little bit different from the internal lock implementation in Gluster for range lock. So we have like in total we have three types of locks. So it is entry locks, inode locks, and POSIX lock. But these are the internal locks. There are only two internal locks. And the POSIX locks is considered to be external. So that is what I was trying to mention here. Okay, so so the inode locks. So basically, if you, let's say you create something like this, okay, when you do ls-l on this file, you have this much size. Okay, you can depict this file like a line which is starting from 0 till this size as your line, and you can take locks. So I can probably show you how to visualize it. So basically this is your file range. Like in this case, because it is 1 MB, the starting point is like 0, ending point is 1 MB. If you are going to modify, let's say first let's say 128 KB. So you take a lock from 0 to 128 KB, do your modification, and then do an unlock on that range. Similarly, if another client wants to take modify something like maybe some 256 KB starting to, let's say, some 512 KB, something like that. It's something like somewhere in between. Then also you can take this lock, like modify whatever you want, then you do an unlock. So everybody who's trying to do a modification will need to take the appropriate locks, that the regions or the data sectors that are going to be modified, you take a lock to prevent other client to modify that entity at the same time. So that's what you do. So this is called inode lock, and because the locks are always on ranges, they are also called range locks. These are like internal inode locks, internal inode range locks. So that is how this inode locks work. All right, so POSIX locks also is also a range lock. We will discuss more about it in the third session. Okay, so now that you know that we can take locks, there are like each translator in glusterfs has to expose this functionality as part of a fork. So these are the forks that locks translator exposes for locks functionality. There are other forks also it implements, but these are the ones that are corresponding to locking. Okay, so inode LK and finode LK are the range lock variant that we just discussed. One is based on the location, that LOC_T date structure that we discussed probably in the second or third session, or maybe in the first session. I don't remember exactly. But this one is based on the FD, the same operation on the FD. Similarly, entry LK is on LOC, F entry LK is on FD. LK operation is based on the system call, that FCNTL system call external thing. It is always based on FD, so there is only one fork. Okay. Yeah. So the other thing is these locks are like resources that the bricks are remembering. Like if you take a lock, let's say for example, when we are trying to create this C, you took the lock, but let's say before you are attempted this create operation of this C, if this client for whatever reason disconnects or dies, if that machine goes down, whatever, all the logs that are present from this client should be released. Otherwise, you have like this operation, this mkdir A, which was okay. This was what, touch C, right? Like maybe mkdir C. Let's say here, if you do mkdir C after this touch C, and this mkdir C will hang because that lock was there. If you don't release that lock, this operation will hang on that. So all operations that are trying to access that same name, like modify that same name in that directory, they will all hang. So it is very important to unlock the resources that were granted to the clients on the client disconnect. So this is also one more thing that locks translator does. Okay, so some terms that we need to understand before we discuss about the locks. So client is any process that is trying to take a lock. Okay, so any process, it's generally like either your client mount process or an internal client process like self-fill daemon or rebalance. But within the brick also, if you want some sort of serialization, you can still use it within the same process. So the client can be anything that is going to call inode locks or entry locks. Okay. Okay. So this lock owner is a number or like a UID, or like it's some way to differentiate two locks within the same process, rather within the same client. Okay, so you identify a lock uniquely as a client and LK owner. Client plus LK owner is what you consider. So between two clients, you can have same lock owner and it is still fine because the clients are different. But if it is in the same client, lock owner must be different. So this is something the clients have to guarantee for the functionality to work correctly. So these two are really important. Then the next thing is domain. Okay, so domain is like a way to differentiate between the purpose of taking the lock. For example, let's say you are trying to write to this file C, like two files are two mount processes are trying to write to the same file C, and they both should take the lock in the same domain because they both are trying to modify the same file. And generally, because this is done by replication, it is replication translator's responsibility to make sure that the lock is taken in the same domain. But now let's say at the same time, let's say this C also needs to be healed. Okay, then like two servers may try to heal the same file, in which case they both need to synchronize also, saying that, I will take care of the responsibility of healing versus the other person. And so even then the locks will be in self-heal domain. So generally self-heal domain, because it's also modifying the data, it takes two locks, one in self-heal domain and another in IO domain, because it's also modifying the actual content of the file. So that is how you can differentiate between two domains. It's generally like you are trying, it's like a namespace in your normal lingo, where you want to separate the concerns about why you are doing that operation or the where you are doing the operation. So that is what is domain. All right. So yeah, so we will try to see how this inode LK behaves. So like we were discussing, if you consider this to be like a 1 MB file, 0 to let's say till 1 MB. Now if you take locks that are non-overlapping, the ranges are non-overlapping, then there is no conflict. It is very simple. You just grant whoever takes this lock. That's easy. Now let's say the two clients, client 1 and client 2, they want to take a lock that is overlapping. Okay, so this can be like this also. Like it can be like one can completely overlap with the other and only partly and all that. That depends on the ranges that the client is trying to modify. So when there is an overlap, then if the client plus lock owner are different, or like either the client or the lock owner, any one of them is different, then they are conflicting locks, because you should not allow locks to both of them. Otherwise, there is a chance of data corruption or replica inconsistency, where one replica will have some data, another replica will have some other data, because you granted the locks to both of them. So to prevent such scenarios, you only grant it to one. The other one can either fail if it is like a non-blocking lock. If it is a blocking lock, then this one will linger on until this guy gets unlocked. So there are like two types. You have both the blocking locks and non-blocking locks. I think in mutex there are in pthread mutex similar concept. I think this is implemented from pthread mutex. I think something like pthread mutex try lock versus pthread mutex lock, whereas try lock is like a non-blocking lock and mutex lock is like a blocking lock. Okay, so the other interesting thing is, let's say if you have the ranges overlapping, but they are from the same client and the lock owner, then you grant this also. So this is how the behavior is. So actually, when I first joined, it was only these two. This was introduced maybe in 2011ish. Yeah, I think 2011 or something. To handle the self-heal plus they wanted to do, I think, granular data self-heal, in which there was a pattern where if somebody already has a lock, we need to give that lock. So this behavior is introduced, but I think at the moment there are like no clients use this part of the behavior, I think. Maybe eager lock in some cases, but it's not something that can happen that easily. All right. Okay, so this is the behavior. Now I think we can start looking at the code. So before I start with the code, are there any doubts in the concept so far?
No.
Okay, all right. Okay, all right. So we can probably start looking at the one fork, which is like inode LK fork, and then some data structures that actually gives you this functionality. Let's dive in to the code. This font size is visible.
Yes. Yes. Yes.
Okay. Let me just do trivial. Okay, so these are the forks that Lock Translator implements. All of these, quite a few of them, but the ones that we are interested in are these. These are actually even flush is important. Like if you take the FCMPL locks, which are the external locks that the applications can take, and if you close the file, the lock should be unlocked. So even flush is important that way. But yeah, so these are the ones that are implemented in lock. Those are like the main forks in Locks Translator. So let's go to PLI node LK. So the PLI node LK and PLFI node LK are like same forks except for the LOC versus FD. So other arguments are same generally. Okay, so let's look at the common inode LK. Okay, so this is some special handling that is there for some backward compatibility. Let's forget about this one. I think we can start from here. So this is like the client. The frame root actually has a way to, it has a pointer to the client using which these locks are sent. So we can have something called as a client context also, which I think I discussed about this in one of the earlier sessions. All the client specific data you can store in this client context. This probably you guys have already figured it out. So because whenever the client disconnects, we need to clear all these logs. We kind of need to remember that on this client, these are the logs that are stored. So you kind of maintain that information somewhere. Okay. The second thing is again the inode context. This is something that we covered in inode_p session. So all the logs that are granted, that are blocked, etc., are all stored in the inode context structure. So this PLI node is the main structure that holds this information. So we can go through this information. Okay, so DOM underscore DOM list. This is like the list of domains. So it maintains the list of domains that are available. So every time you take a lock with a domain that doesn't exist, it will create a new domain and it will add it to this list. Ext list is like the external lock maintenance. These two are related actually. These I think we probably don't need to discuss now, because I think they tried like reserve LK concept, but I don't think it went anywhere. So this one we probably don't need to look at. This is something that we will discuss in the next session. This is a recent addition to improve performance. We will discuss about this in the next session. Mandatory locks, I don't think we use that much. I think it was introduced for DHT mainly. But I don't know whether it is in use. Amar, do you know?
Not using it right now.
Okay. All right. So, all right. Okay. So, yeah. So these are all related to the maintenance of some metadata related to the logs. But the main things that we are interested in internal logs is this down list. This one will have the information. Somebody thinks something. Manuals are part of LK call itself, but we don't support it. Okay, cool. All right. Okay. So this like per inode, whatever is context is POSIX logs translated stores, that is going to be in this. So we get that data structure. Then we get the domain that this lock is the lock request came on. So this is again a data structure that stores the domain. So this is interesting. So you basically have like the domain name. Okay, like now I think this is pretty simple. Like you have entry LK list is like the ones that are granted. Blocked entry LKs are the ones that are blocked, waiting for the unlocks to happen on some of the logs that are there in entry LK list. Similarly, inode LK list is the one that are granted. Blocked inode LKs is the one that those are waiting because they are conflicting with the ones that are granted. So they are maintained this PL DOM list. Okay. All right. Then, okay. So now from the given arguments, we actually create this inode LK request. So let's try to figure this one out. This is the inode log structure. Most of these things will be self-explanatory. So this list is like the granted list, which is maintained to hold all the logs that are blocked. So either this one should be non-empty. I mean, like this object is. Oh man, I've become hook guy. Okay, this structure is supposed to be either in a granted list or blocked list. There will be a small amount of time where it will be in both blocked list and granted list to make sure some unwinds happen correctly, etc. But the generally, like if you look at it from for some time, it will either go into this list or this list. This contention list is for notifying that. So there is this concept of eager locking in both AFR, which is like the replication module, and in erasure coding, where they will like instead of taking the lock and for every operation and then doing an unlock, they'll just take the full file lock, meaning 0 to infinity they will take, and like it will do the ordering of the writes. So if the writes are conflicting in the same mount, they will send one after the other. If they are not, then it will send all of them in parallel. So when you are taking lock for extended periods of times, if another client requests for this lock, you need to tell this first client which has taken the lock and which has been holding this lock for a long time, saying that there is a contention detected. Please unlock as soon as possible. So to maintain that, this thing is introduced by Zavi, I think. Okay, so this is like the reference count for this structure. Start and end are they are representing the range. Okay, so this is the full structure that has come from the user. This volume represents the domain. Maybe we should just call it domain to avoid any confusions. This PL inode is like a pointer to the inode context which this inode lock is going to stay in. This frame is the request frame. This is very important actually. Block time and granted time. Like if this is useful to identify if there are any stale locks. If your granted time is like 1 day old, then you can 100% it's a stale lock. If your block time like it is like more than like some minutes old, most probably there is a deadlock somewhere. So yeah, so this is the same thing like when the contention was detected and notified. These are all like for debugging purposes. It doesn't really serve any functionality in logs. It's mostly for when you take a state dump, you will know what is the status of some particular inode with respect to logs. This actually is for the client related information. The LK owner, this is actually your lock owner. Then these are your connection IDs and PIDs. This is like the string form of the connection. List of all lock. So yeah, so I was mentioning, right? So every time a lock is granted from one particular client, it has to be added to that client context. So this is the list of all the clients. Sorry, all the locks that are in particular client. So this will also be non-empty generally. The log type can be like read or write, but at the moment, all the logs that are done in all the internal logs that are done are all write logs, because you can reuse it for both reads and writes. You don't have to like unlock and then take a write lock or try to upgrade the logs and all that. Because we also have this contention logic, we only use mostly write logs. So this is like, it represents the error condition. So yeah, so this is like the main data structure of the locking. Okay, so now that we have, so once we have the lock structure, you have like, the other logic is reasonably self-explanatory. So if this command that you get in the input is LKW, which means lock with wait. LK means lock without any waiting. So basically this is non-locking and this is blocking. So now comes the main inode lock code. So now you will see the logic that we discussed. Okay, so yeah, so this is a feature. I think at some point Facebook guys were facing locks that are stale and either stale or deadlocked, so they did not want to deal with. I'm like in prod workloads, they did not want to wait for fixes to roll in, so they implemented a feature where after a certain time you just unlock all the locks, because you generally know that if a lock is more than like let's say some 15 minutes, you know that it is stale lock or like there is some deadlock. So they implemented one feature to do that. So yeah, so this is like for the contention notification, so it will do something here. Anyways, so this is like your main the decision maker. So this part I think we will cover in the next section. So this is the like those 3 slides that we discussed. Is it like a conflicting thing? Is the inode LK owner same or not? So these are the 2 decisions. Like for all the locks in the granted lock list, you go through each one of them and see whether the inode LKs are overlapping or not, whether one is read lock and another is write lock. At the moment, there won't be any read versus write because we only use write, but it is there for like, in future, if somebody wants to do something, this functionality is already there. Okay, similarly, you have whether the client is like same inode elk or not. I was mentioning, right, these two have to be same, like the client has to be same and the owner has to be same for it to be a same client. So if both of them are like, if there is a problem with this, then like, you found some conflicting log. So you say, okay, I have detected some conflicting log, and like, you also kind of notify the client saying, hey, some contention is detected. So this function actually handles that one. So basically it will put this into that content queue, so that some other like you basically send an up call. So there is a concept of up call in glusterfs server where you can notify clients about some events. So this goes into that logic. Yeah. If like, so you now have to decide whether it is like a blocking lock or non-blocking lock. All right. So if it is a non-blocking lock, there is nothing to do. You just say, okay, this is not going to work. You will return some error called E again. But otherwise, you kind of add it to this block blocks list that we discussed. You also say this is the time at which the block is blocked. This is for debugging purposes. All right. So yeah. So if it is like you are returning basically E again, which is like try again. Okay. And then if like, you don't have any like, conflicting lock with the granted list, now you have to also check with the existing blocked locks to see if there is any conflicting lock in the blocked list also. It's the same thing basically. I know delta config, it's just like the same function that we have discussed. Overlapping and like right lock, these things. So you basically you put this again, like, basically this is like the same check but with block blocks. If there is a conflict, you have to put it in block blocks because you have to give priority to the ones that are already blocked. So basically, if there is a conflict, you are going to put it in a queue so that first come first serve is maintained. So this is again the same thing. All right. If it is not conflicting with block locks also, then you like, okay, we are ready to grant this lock. So you just grant the lock and put it in the granted list of that domain. So now everybody is happy. All right. So this is for locking part. If let's say the command that we got is set lk with unlock instead of right lock or read lock. Let's say if it is unlock, then I think this is important. So this part is the one which adds this lock into the list of logs for that client. Okay, so this ctx here is like the client ctx. Where is that? Yeah, plctxt. So this is like the client context. Where are you? Okay, yeah. So this is the one. This is like the client context. All right. Now this is again back to your unlock. So like unlock, I think you guys probably have figured it out by now. So like it will be like once you get a lock granted, you do whatever work you want to do, and then the client will send an unlock. Similar code path gets executed like we had before, where it will create a lock request out of it. But because it is unlocked, now this code path gets executed. So basically, you need to find a matching inode lock, which is again the checks are same. Like inode the range locks have to match, and the owner has to match. When you get that, you go and you delete that unlock and remove it from the locks. Then there is like you have to grant the blocking lock. Where is that? So whenever there is an unlock, you have to check whether there is any of the locks that are blocked that can be granted now, because they've been waiting for something to get unlocked, right? So you go over all of the block locks and in that order and see again. You try to do this inode block, inode block, inode block. And, so yeah, that's what happens here. Okay, so this is what happens with the both locking and unlocking. Before I move on to, okay, wait, I think is that the one? Yeah. So this is like the high level code walkthrough of the inode lock. When we go through entry lock, the concepts will be exactly same, except for the range lock checking, it will do the name lock checking. So I'll cover that part in the next session, along with this extra functionality of like some optimization that Zavi did in one of the patches. That we will cover in the next session. Let's okay. So are there any doubts till now?
Not much, but I need to start going through then maybe. Yeah.
Okay. All right. Then the only other thing that we need to cover here is the disconnect code path. So we have covered inode lock T, domain list T, code walkthrough. Yeah, clearing the locks on disconnect. Okay, so this is very important to not have any blocked locks. So where is this? Yeah. So this translator actually registers a callback whenever there is a disconnect from a client, and this one will get called whenever there is a disconnect. So it will basically all these resources like inode lock, entry lock, and there is a concept of meta lock also, which I don't think gets used that much, but yeah. So all the resources that are granted, you have to do a cleanup. So here we are basically, so the work that is cut out for this function is something like go through all the granted locks, unlock them, go through all the blocked locks from this client, and just unwind them, saying that E again or E not count, one of the two, I think one of these two it will do. So that's what it will do. So for each lock in this the list of locks that are in this client, it will go through the if it is a granted lock, then you are just going to delete this lock. If it is a blocked lock, then you kind of gather all of such blocked locks so that you can unwind. That's why it is gathering this all of these things into this unwind list. This is the unwind list. Okay, and once this process is done for each of the list, each of the locks that are in the unwind list, it will keep doing this stack unwinding, saying that you have to try again, but the connection is already dropped, so it is more like a cleanup basically. So what? Yeah. So once you have cleared some locks, then you have this extra step of granting the locks that are blocked, because whenever a disconnect happens, there is this chance that some granted locks are unlocked. So you go ahead and grant the blocked locks, which is like similar to the one that we saw before. So yeah, and then there is also this contention notification, which is the same always. Every time you see any contention, you kind of have to notify. But yeah, so this is mainly the gist of what happens in inode block. Are there any doubts, guys?
No, no.